Hello, everyone. Thank you for attending the Accelerating AI with UALink Open Memory Fabrics for Scalable Compute webinar. Today's webinar will be led by Ronan Hyatt, CEO and Chief Architect at UniFabrics. We'll go ahead and hand it off to Ronan now to kick off the webinar.
Thank you, Nolan. Hey, good day, everybody. Good morning, evening, afternoon, whatever your time zone is. Happy to be here. I'm the CEO and Chief Architect of UniFabrics. We are building silicon, which is fabric independent around UALink for connectivity, switching, and memory. So we'll start with an overview of UALink, and we'll jump later to some of the challenges that exist today with AI clusters, in particular around memory and how this can be solved over UALink, which is an open ecosystem which enables innovation. So UALink is an open, high bandwidth, low latency interconnect, and it connects AI accelerators such as GPUs. GPUs is one type of an accelerator, and switches within a compute pod or a cluster. So what we see here is a typical topology of a UALink cluster. We have the accelerators and the switches, and we see multiple planes where each accelerator connects to the other accelerators via one or more UALink switches through different ports. We see hosts that have their own memory, DDR. The accelerators typically have HBM, and we see the UALink links that connects the UALink domain. So one important aspect about UALink is that it is open. It enables to use any UALink switch and any accelerator from any company. It's an open standard, and this is the reason it enables multi-vendor innovation, which is so important in such a large ecosystem. UALink supports different physical layers. One physical layer is based on Ethernet using 200G serials, and there is another variant which is based on PCIe running at 128 gigatransactions per second. So both are supported. Some important milestones around the UALink timeline. May 2024, the promoter group press release was out. If we look at the specification published, we see April 2025, the UALink 200 1.0 specification published. This is based on Ethernet physical IEEE 802.3DJ, and the variant based on PCIe UALink 128G, the data link layer and the physical layer, which was published in September 2025, which is actually based on PCIe 6.4 with extended speed mode at 128 giga transactions per second. Some of the consortium members of UALink, and here UniFabrics at the bottom of the slide. So let's deep dive into the typical connectivity landscape when it gets to AI cluster. So this is a typical cluster based on UALink. We see the accelerators, and as I mentioned, accelerators could be GPUs. This is one type of accelerator. These accelerators have their scale-up fabric or a network. Sometimes this terminology is interchangeable, meaning some people call it a fabric, some people call it a network. A fabric is typically a special type of a network. We see the UALink switches that connect the accelerator, and this is the scale-up domain. The accelerators typically connect to host CPUs or hosts, and this goes over standard interfaces such as PCIe, CXL, ARM-Chai, Infinity Fabric, or other types of proprietary interfaces. Behind the host, there could be a CXL memory pool. And this is important because UALink can get other types of protocols involved into the ecosystems, such as around providing memory to the cluster. So what is the meaning of scale up? Scale up really means is that we keep the same semantics when we grow the number of accelerators. UALink is a memory semantics fabric, meaning it runs memory transactions. And when an accelerator runs the workload that it runs, it's usually uses loads and store to access its own local memory. When we're using scale-up fabrics, it means that this load and store semantics actually extends beyond a single accelerator. So one accelerator can actually access, read and write other memory in other places on other accelerators. And the memory behaves as if everything is coupled to the accelerator itself, meaning the software remains the same. And this is practically the meaning of scale up, because when we go scale out, and one example of scale out here is Ethernet. It could be InfiniBand as well, but Ethernet is very common. When we go scale out, we actually replace the semantics. It's not memory semantics anymore. It could be verb semantics with RDMA, InfiniBand, or it could be socket semantics for TCP/IP, or it could be other types of semantics, network semantics, where we pack some data. It could be a large DMA transaction of moving a memory chunk from one place to another, but it doesn't go through loads and store, not through standard loads and store. The host side here with CXL could also be considered part of a scale-up semantics, but it goes into a different protocol domain. There are other protocols involved in the AI cluster world and ecosystem. Some of them are very known, such as NVLink from the NVIDIA world, and other attempts to take Ethernet or Ethernet physical layers and use it for the scale-up domain. Most recently, it was ESUN, Ethernet for Scale-up Networking, or SUE, Scale-up Ethernet, which takes the property of Ethernet as a great encapsulator where people can use Ethernet to pass memory semantic transactions, but their Ethernet actually serves as a container, as an encapsulator for the memory transaction itself. Moving forward, so UALink creates the scale-up pod. This is an extension of the previous slide. UALink provides a high performance, up to 800 gigabits per second per port for 4 lanes of 200G, scalable ports per accelerator, the number of ports up to 1K accelerators and more than 1K going forward. It's a low latency. It's an optimized protocol, transaction, a link layer, and physical layer. It provides low power because of the simplified UALink stack that can enable silicon designs that use lower power. And also it enables smaller die area because it provides an optimized data layer and transaction layer. So this saves significant silicon die area. UALink 1 focuses on single tier switching. So if I go back to the previous slide, what we see here, we have the accelerators, we have the switching tier, and there is only one switching tier. So there are 2 hops from one accelerator to the next accelerator. Let's go over the basic terms of UALink. So UALink is an interconnect. The building blocks are accelerators, such as GPUs, the switches, the hosts. It's a memory fabric. The transactions involve memory. It uses memory semantics. It provides the accelerator to accelerator communication. And the initial focus is sharing memory among accelerators. So here in the figure below, we see accelerators that have their own HBM memory, high bandwidth memory, and each accelerator can go and read and write memory on an HBM of another accelerator. And it can do so with UALink using direct load, store, and atomic operations between accelerator at low latency, high bandwidth, a large number of accelerators. We mentioned 1K and going forward, and simple load, store, and atomic semantics. It's not cache coherent. It's different than how CPUs typically communicate with each other. It's software-based coherency, which is much simpler, and it enables to simplify the system and simplify the silicon design. We also have here a system node or an OS domain, which is typically one or more host CPUs and one or more accelerators connected to each other. And this goes typically via CXL, PCIe, or other types of interfaces that connect hosts to devices. So we see here first accelerator in a first system domain connected via UALink switch to a second accelerator that's in a second system node or an OS domain. Usually in a system node, we have a single OS image, and usually the communication within the system node is coherent, meaning cache coherent. So the accelerator to host connectivity, for instance, could go via cxl.mem or cxl.cache or ARM-chai C2C, and it would be coherent. If something changes on the system, like if the host tries to write something, the latest value, the latest copy of the data is automatically available to the rest of the devices, the rest of the accelerators that look at the same address. This is cache coherency. Some of the benefits of the UALink 200, the 1.0 specification, mainly about performance, power, and efficiency, the low latency, the high bandwidth interconnect, the same row speed as Ethernet. Ethernet typically uses the highest available type of SerDes. Today it's 200G serial, and it's growing rapidly to higher speeds. And with the lower latency of PCIe switches. So UALink actually combines the high bandwidth of Ethernet with the lower latency, which we can find in the PCA and CXL. High efficient switch design, reduced power, reduced complexity, small packets, fixed fleet size. It helps designing a switch. ID-based routing, meaning each of the accelerators, each of the entities that participate in a UALink fabric has its own ID. And switches and accelerators, when they have to decide how to route a message, a packet from one place to another, it uses this ID to bring the packet to its place. The word simplicity repeats multiple times. This is one of the design goals of UALink. It helps a lot in creating multi-vendor interoperability. Everything is simple, everything is well-defined. The silicon die size is significantly smaller. The power is smaller, acquisition costs, and the bandwidth of efficiency. The standard is open. And as I mentioned, it enables innovation, and it enables using a lot from the Ethernet ecosystem and the Ethernet infrastructure. The cables, the connector, retimers, management software, and more from the Ethernet domain, since it uses the Ethernet physical layer. Now, going even deeper into the stack, this is the protocol stack of UALink. We see here below the UALink physical layer, standard Ethernet PHY, with some tweaks that are particular to UALink, supporting 200G per lane, also possible to support other Ethernet speeds, with the FEC for the error correction, the PMA, the PMD, and going upwards to the data link layer and the transaction layer, where we have fixed payloads, 64-byte fleets at the transaction layer, 640-byte fleets at the data link layer, with the link layer retransmissions that enable reliability on the link. If something bad happens and something doesn't get correctly to the other side, there is a way to retransmit the fleet, retransmit the contents, so it's not lost. Credit-based flow control, management of the buffering, and same address ordering, meaning if you send something, although there are multiple links and there are multiple paths that connect one accelerator to the other, The UALink scheme keeps the address ordering, so you know exactly the order of what comes first and what comes next. Cable length up to around 4 meters. The request to response round trip time below 1 microsecond. Pretty good latency. Up to 4x, 1 to 4x, around 1K or more endpoints. And the basic units are requests and responses, and it has end-to-end encryption and authentication. Looking at the protocol stack end-to-end, we see here an example of two accelerators talking with each other, or accelerator talking to another accelerator via a switch. And these are the protocol stack layers. There is the UALink protocol level interface, UPLI. You would be working with UALink Silicon. You would be working a lot with UPLI. UPLI is a point-to-point on-chip interface that is comprised of various channels. Here we can see the channels: request channel, originator data, read response data channel, write response. And UPLI is the actual protocol format that powers UALink and does the operations that we talked about. If we look at the command set, and this is part of the command set, you can find the whole command set at the UALink specification. You would see here, for example, a read command that uses the read response data channel to get the data back. And you would see a write command that can write up to 256 bytes. And it's using the originator data to pass the write data from the UPLI originator to the UPLI completer. And there are other commands. Some of the commands are vendor defined, so UALink allows a lot of innovation. If someone needs to define new commands, this is already built into the UALink framework, very easy to add. And UALink itself provides quite a comprehensive set of commands to use. Looking at some of the typical topologies that UALink can use. So this is one example of a switchless topology. Usually it serves a small cluster up to 8 accelerators. Here we see here the 8 accelerators interconnected between themselves. Sometimes this type of topology is called a hybrid mesh cube or other variants of this name. We have the 4 accelerators fully connected to each other, and there are other 4 accelerators, and there is maximum of 2 hops between an accelerator and another accelerator. Let's take these 2 examples. This accelerator here at the top left, trying to access the bottom right, goes through 2 hops. This type of topology could have 1 or more hosts that could connect to the accelerator over CXL or PCIe or other types. We mentioned ARM Chai C2C as one example. And different accelerators could be within the same or within different OS domains. So this is a very simple topology, but it's a small one. If we want to grow into larger topologies, we go into a single layer switching. We have here N switches, N UALink switches. And in this example, we have N ports on the UALink accelerator, and we see multiple planes. And each plane connects all the accelerators and provide full connectivity between the accelerators. And the reason that we have multiple planes, first of all, it provides extra bandwidth. We could reach from one accelerator to another through multiple paths. It also serves us for fault tolerance. Sometimes bad things happen, links go down, switches go down, but the system keeps functioning because we have this redundancy. And having multiple planes could also help us create a logical separation. Could be, for instance, between different tenants in a virtualized environment, or for different types of traffic that would go over different planes. So here we have M accelerators. Each accelerator have N ports, and we have N switches. This is a bit simplified representation, since each of the ports may have multiple lanes. It's not necessary that the port is a single 200G lane. It could be 1, 2, or 4. So the diagram itself could be a bit more complex than this, but this one is a good representation to get the understanding how the topology looks like. So why UALink is important? And I believe today everybody understands the term, the AI memory wall, and the pace of data, and the widening gap between compute, memory, and I/O fabrics. It's evident then that compute grows much faster than the memory bandwidth, which is provided by the memory components or the memory systems, and the bandwidth provided by the I/O and the fabrics. And this is one big problem that the whole AI community is dealing with. And UALink as a memory fabric addresses exactly this gap. We have the compute, the GPUs, the accelerators, and UALink as a memory fabrics brings us the connectivity, the high bandwidth, low latency connectivity to memory, and as much memory as we can get, and being able to connect more memory, meaning that we can have more bandwidth going into the accelerator, into the compute. And it's also improved the fabric aspect, because the fabric is the transport for these memory transactions, the connectivity between the accelerators. So UALink does exactly that. It addresses the memory wall and tries to bridge that gap. And what we can actually claim here is this is important because AI inference is really a memory problem. And what we see today, especially with LLM reasoning models that drive memory pressure up, and agentic AI that needs a lot more memory, that the problem becomes less compute and more memory. And part of the reason that we need these scale-up AI fabrics is because the problem size itself is too big to fit into one GPU or one accelerator or one HBM or the amount of HBM that exists on this accelerator. This is why we need the scale-up fabric, so we can grow and build something that looks like a big GPU, which is made of multiple GPUs, multiple accelerators, but they all behave from the software side as one big element. So, for instance, if we look at the KV cache, it dominates the memory footprint at long contexts and with batching. And if we take, for example, Llama 3, 70 billion parameters, 128K context, the KV cache is around 40 gigabytes, which is quite a lot. And the KV grows linearly with the sequence length and batch size. And this is really driving memory pressure up fast. We see here on the right the context window, and the context window has been growing quite significantly. And the number of tokens that exist in the context window really translate to the amount of memory that is needed in the system. And this is per one conversation. And assume that we have multiple tenants in any environment that are doing conversation with the model. So the amount of memory is growing to many terabytes, and this becomes a real problem. So KV caches can be typically stored in GPU HBMs, and HBMs, the high bandwidth memory, is the most expensive and scarce memory resource of an AI infrastructure. And the bigger memory footprints actually force us to do a multi-GPU sharding, meaning take this amount of memory footprint and partition it across multiple accelerators, multiple GPUs. And this actually adds to the communication and synchronization overheads. It lowers efficiency. This is how we get lower GPU utilizations. And at the bottom line, it contributes to the higher costs of AI inference. So memory is a problem for AI inference. but memory has just recently become even a bigger problem. And I think everybody know at this stage, because we see the headlines every day of what's happening in the memory market, the prices keep going up, and memory has become an expensive of a very scarce resource, where HBM puts a heavy pressure on standard DDR5, and we've seen some of the vendor actually exiting the consumer market. Micron has done that just recently. I was surprised to see some of the graphs, how steep they are in the last months. So this is becoming even a larger problem than it used to be in the past. Let's look at the memory resources that are available to us in a typical AI cluster. So the first one is the accelerator local domain. And here we have HBM, high bandwidth memory, which is the most expensive DRAM type. It's a dynamic memory. It looks like DRAM, but it's the interface is much wider and provides a lot more bandwidth, but the latency is very similar to DRAM. HBM is limited in capacity, sitting within the package. So even if we build it using multiple stacks of multiple dies of DRAM, it's still limited in capacity. What's the next one in? What's the next type of memory? It's the DRAM on the hosts. And we have here the hosts with the standard DRAM. It could be a DIMM form factor. It could be CXL memory. And this could be expensive too. If we look at some of the super chips that exist in the market, where we have a GPU and a CPU on a super chip, and the footprint, the physical footprint of the PCB is not that big, even the DRAM that sits closer to the CPU is 3D type TSV stacked DRAM, which makes the DRAM expensive as well. And expensive means it could be 5x to 10x, sometimes more than the cost of mainstream DRAM. We also have optional CXL memory that can provide additional bandwidth and can also provide additional capacity. But usually this type of connectivity in typical systems, is limited by the bandwidth of the host to accelerator or CPU to GPU interface. So if we look at PCA-based systems today, this is a major bottleneck. The accelerator, the compute, has a lot of bandwidth from its local HBM memory, but once it tries to get to the host to get extra bandwidth and extra capacity, there is a significant bottleneck over this interface. Another issue with this type of memory on the host is that it's asymmetric. It's seen differently. It behaves differently when it is viewed from different accelerator. For instance, if you have accelerators that are connected directly to a host, usually you will have pretty good performance, as much as you can get from this local interface. But once you need to go to a DDR that sits on other hosts that connect to other accelerators, and this is where you need to go through the scale-up fabric, through the UALink switches, this is where you get an asymmetric view of that memory, because the bandwidth would drop and the latency would be much higher. And in the next slide, we will see some example of real systems, how things work in existing AI clusters. And also this memory could be limited in capacity. And I mentioned the super chip, which is limited in the PCB footprint and the amount of memory that can sit on that super chip. What's the next tier? And usually the next tier goes to something which is not really memory. It could be storage. And there are quite a few implementations that support KV caching using storage. And there are some implementations that use NICs or RDMA to fetch memory, not through the scale-up domain, but through the scale-out domain, meaning you would use a NIC here to fetch via RDMA memory that exists on another host. So it would be available on a host closer to the accelerator that consumes the memory. So this is a kind of a compromise. So just because memory resources are limited, people are looking for ways to get to memory through other means. If we look specifically at the scale-up domain, and we want to see what performance we can expect there, there is public data about existing AI systems based on NVLink, such as the Grace Hopper superchip. And what we see here, this was presented in Supercompute just a month ago. So what we see here is the memory view from the GPU from Hopper and the memory view from the CPU from Grace. So as long as it is local memory, the performance is good. We see HBM on Hopper, the bandwidth is pretty good. We see here almost 4 terabytes per second. This is one variant of the GPU. The latency is below 400 nanosecond. And this DDR is the DDR of Grace, the CPU that connects to the GPU. It provides additional bandwidth, higher latency. But once we go over NVLink or NVSwitch, the performance drops dramatically. If we go to the HBMP, the peer superchips, like the peer Hoppers and the peer Grace that exist across the NVLink switch, the latency grows beyond 1 microsecond for HBM and even higher for the DDR, and the bandwidth drops significantly. And this is one example when I mentioned that there is an asymmetric view from different accelerator. You could see that one GPU, when it accesses the local DDR of its adjacent host, it gets one performance. When it tries to access another DDR on another host through the scale-up domain, the performance looks completely different. From the CPU side that connects to the GPU or the accelerator, there is the local DDR of the CPU. And here we see typical performance of CPU local memory below 200 nanosecond for latency and bandwidth, which is around 0.5 terabyte per second for 500 gigabytes per second. When the CPU accesses the HBM of the tightly coupled the closed GPU, the latency grows higher, the bandwidth is okay. And trying to access over the scale-up domain, here the latency grows and the bandwidth is getting smaller. And this creates an opportunity for innovation. And UALink practically unlocks the scale-up domain as an open standard, and it allows multi-vendor innovation. And we at UniFabrics bring memory as first-class citizen in the scale-up domain, meaning we bring high bandwidth, high capacity, on-demand memory tier, and we provide independent scaling of memory and compute. So what we do in UniFabrics in the context of UALink, we actually create a memory switch tier, which is available in the scale-up domain natively via UALink as a UALink memory. You can look at it as a UALink memory pool or a UALink memory expander. It's native UALink, and it's available to all accelerators. And it actually looks symmetric, regardless of what accelerator you're using to trying to access it. And the silicon that the systems that we build have dual personality. We build a memory switch around the scale-up memory-centric architecture. And the dual personality means that this silicon or this system behaves as a UALink switch, and it can also behave as a UALink memory pool. And depending on the implementation, one can choose to have it as a switch and memory. And this is the typical topology that we saw previously with the UALink switches. And now we have the UniFabrics memory switches, which act as a UALink switch, but have memory connected to them. And that memory could be mainstream DRAM, meaning standard DIMMs, mainstream memory, or it could be CXL memory. We support both. And this is how we bring memory into the scale-up domain. And this memory is accessed natively by the accelerator, meaning any load and store that an accelerator can do to its own memory or to a memory that sits on another accelerator, it can do to the memory switch. In fabric memory, the memory is part of the fabric. And here memory becomes as a first-class citizen in the scale-up domain. It's native UALink, it's fabric-attached memory, and it has symmetric view from all accelerators. In terms of capacity and bandwidth, this can bring tens and of terabytes in a single memory switch instance, and we can have multiple of those. So within a pod level, we can get to hundreds of terabytes, which is quite a lot of memory. And the important thing is that this is mainstream DRAM, meaning it also significantly reduces the cost of memory within the system. In terms of bandwidth, it's HBM class bandwidth per memory switch instance, meaning each of these instances can provide above 1 terabyte per second. And once you have multiple of these within the system, it could be multiple terabytes per second of memory bandwidth. So this is how it looks as when it functions as a memory switch. Now we look how the system looks like when it functions as a UALink memory pool. This is the other type of personality. So the upper part of the diagram is a standard UALink topology where we see the accelerators and the switches. And now we have UALink memory pools that are connected to the UALink switches as a scale-up memory tier. And just as in the previous example, this memory is accessible by all accelerators using standard loads and store, part of the memory footprint that each accelerator can see. The memory is exposed natively over UALink. These memory pools have an ID, so they look like an accelerator with giant memory. So when one accelerator accesses the memory pool, it looks like as if it is accessing another accelerator that has a lot of memory. And another representation of this topology looks like this. It's actually the same, just the location of the memory pool. Previously, it was drawn below the UALink switches, but it's actually a native part, a native participant in the UALink domain. So this is just another representation. From a form factor point of view, this is one implementation of a memory switch when it is delivered as a rack level memory node. So one of the options is to install it as a standard rack level device. It has ports at the back. We support UALink, we support CXL, we also support Ethernet. So this can do switching between the accelerators themselves, or you can connect to UALink switches through these ports and have the memory delivered to the switches and from the UALink switches to the accelerators themselves here in this model. This is the appliance. It connects to the UALink switches and from there to the accelerators, or it can serve as the UALink switch itself and connect to the accelerators directly. It's depending on the size of the cluster and topology that you choose for a different implementation. We call it memory over fabrics, and it was awarded as the most innovative technology in FMS in last August. A single instance can support up to 32 terabytes of mainstream memory, and it uses standard OSFP cabling. It can come in other form factors. The standard memory node as an appliance is the one at the top. It can also come as a UALink fabric NIC, and this is a new concept, which is platform independent. The silicon that we produce, the FPU, when placed on a PCB card that looks like a NIC, fits into any standard server, and it actually makes the server an active participant in a UALink fabric, in a UALink connectivity, meaning the memory of the server is accessible to accelerators And this memory becomes as part of the UALink domain natively. And the silicon can also fit into an active cable, so it becomes a smart UALink active cable, something that looks like a standard retimer form factor when the cable does the magic of exposing the memory between the servers and the accelerators. And of course, it can come as the ASIC itself in high-end applications. This is the silicon. The silicon is accompanied by software. We call it a fabric manager. This is the standard term. And the fabric manager is actually an orchestration layer that controls who gets what's the memory representation or the memory abstraction that each compute element sees, and how much of the memory that sits in the fabric each of the compute elements can get. And this works dynamically. The fabric manager can provision memory on the fly, deprovision memory on the fly in the UALink domain. And it also works on CXL memory, and it integrates CXL memory natively into the UALink domain as part of the other memory resources. If we go even deeper into the structure, what we built in our memory switch is a memory interconnect controller, and this is a scalable architecture. We can have one or more of these memory interconnect controllers, so we can have more memory channels if required and more ports if required. And here we see the UALink fabric NICs that connect to accelerators such as GPUs. And we can have CXL fabric NICs that connect to standard servers, or even Ethernet fabric NICs that can expose this memory over Ethernet when required. The fabric manager architecture itself controls the behavior of the system, and it can connect to a cloud native orchestration layer where it gets commands from the orchestrator where to allocate this memory. And here we see the interfaces. The interfaces UALink could be UALink to GPUs and accelerator, or CXL to hosts. And the memory from one memory pool or memory switch can be exposed dynamically to this. If we have multiple of these memory switches, the fabric manager controls them all and eventually creates a uniform memory topology, which is controlled by the fabric manager. This is an example of how it looks like on the dashboard. In this example, a single memory pool of almost 6 terabyte with hosts or memory consumers connected to it. Sometimes there would be a single link. Sometimes there would be multiple links for redundancy or for higher bandwidth. And this shows the actual consumption from the memory pool. How it looks like in terms of performance. So these numbers are taken from our lab. We have results from CXL on the CPU domain and from UALink on the GPU domain. On the CXL domain, it's pretty much stable. We've been running it for more than 2 years. UALink is new, so this is prototyping. So the performance is expected to get better over time. And what we see here that on the CXL domain, on a native CXL, we can get to around 400, and below that, between 200 and 400 nanosecond of latency at quite a good bandwidth, 500 and more gigabytes per second using multiple CXL links. And on the UALink domain, crossing the 1 terabyte per second, the latency is a bit higher. Some of this is attributed to the different physical layer, but it's still very good when we compare it to market benchmarking. So a quick recap. What we've seen here is an introduction to UALink as an open scale-up fabric technology, which connects accelerator and switches and uses memory semantics. And UALink puts significant emphasis on simplicity and well-defined protocol functionality, which is crucial for cross-vendor interoperability and enables multi-vendor innovations. And specifically, the innovation that UniFabric brings is memory as first-class citizen into the scale-up domain by the UALink memory switch, which can act as a UALink switch or a UALink memory pool. So thank you very much. And now I'm happy to take questions.
Excellent. Thank you, Ronan. Now we'll go ahead and dive into the Q&A. If you have any questions, please feel free to submit them into the Q&A box at the bottom of your screen. Our first question for today, how does software see the addressing across this memory fabric, multi-node cluster, global uniform addressing? Who manages the allocation and assignment? Is it the fabric manager?
Yes, it is. It is the fabric manager that orchestrates and abstracts the memory footprint. In UALink, there is the notion of an NPA, network physical address, meaning this is the address footprint that one accelerator exposes to other accelerators. And having a UALink memory pool actually means that the memory pool exposes an NPA. So it exposes the memory that it has just like another accelerator. So the fabric manager or something equivalent to a fabric manager orchestrates this abstraction. How much memory is exposed? It's not necessarily the whole memory that exists in the memory pool. It's not necessarily the whole memory that exists within a single accelerator. It's just a representation, an abstraction.
Excellent. Next question, is a UALink port limited to 4 physical links?
Currently, UALink defines as a station that could have 4 lanes, 4 by 200. For example, it could be also, the port could be 4 of these lanes, could be 2, or could be 1. Future revisions of the spec may define other types of ports. Today, it's by 4.
Perfect. The next question, could you please touch on the RAS aspects? How are faults detected and handled? How does the fabric manager or pool switch identify and handle dead or faulty memory chips?
That's an excellent question because RAS is extremely important in this environment. So looking, for example, at the memory switch where we have mainstream DRAM inside, so a lot of the conventions and a lot of the methods that were developed in the server world for providing reliability, being able to do, for example, PFA, to detect imminent failure of memory or detect errors in memory, isolate failing DIMMs, migrating memory from a place which is imminent to failure to another place in a transparent manner. All that is handled in the background transparently, meaning that if the system detects that there is a problem with some memory components, it can migrate the memory to another place and shut down these memory components or DIMMs and remove them from the memory footprint and provision other memory resources as a replacement. And this is all transparent because the consumer of this memory doesn't see it. It all happens in the background. So this is one example where RAS is handled. RAS could mean a lot of things. If you really want redundancy in the memory, so mirroring and striping a RAID-like memory is also possible, although it's very expensive in terms of memory footprint. There is also redundancy on the link side. When we looked at the topology, we saw that accelerators connect to each other through multiple planes. So it can actually reach other accelerators or memory resources through multiple links. So this helps to the bandwidth, but it also helps for redundancy. There is also the link level retry. When something bad happens on the link, the link layer is able to retransmit the data. So RAS means a lot of things, and there are a lot of mechanisms set in UALink and other mechanisms that are built by vendors that participate in the UALink ecosystem that helps make this system reliable.
Excellent. The next question, can you please touch on the capabilities of near-mem processing? What can it do? How programmable is it? And how would a host or GPU use it?
That's a great question. If we look at a typical system where we have accelerators and hosts, and we said that there is a coherent view, typically there is a coherent view between the host and the accelerator. So some of the processing can run on the host itself, and if the memory sits in the DDR on the host itself, when the accelerator accesses this DDR, it actually sees the latest copy of the data. In our specific case in UniFabrics, when we build memory pools, there are near memory processing capabilities inside, meaning there are processing elements here that can touch the memory and do the work. And this goes through a software-based coherency, such as between two different accelerators. This is the scheme which is used in UALink. So there is a responsibility who touches the data when, and such processing can happen in the memory switch and later handed over to a specific accelerator or a set of accelerators. So this is done, and all the mechanisms are in place to support that.
Excellent. And on this slide, we have a question. What is PFA, that acronym there on the left side?
Oh, it's predictive failure analysis. It means that you can detect an imminent failure of a memory component before it happens, before you're actually losing the data. And this is important because if you know how to do it well, you can actually migrate the data from this failing memory component before it becomes inaccessible, and move it to another place, and actually reprogram the memory footprint in a way that the consumer, the accelerator, a host, anybody who's using this memory doesn't even feel it.
Perfect. Next question, what are the unique strengths of UALink that support its quick adoption?
Great question. So ULink was built to be simple and well defined. And since ULink is open, this is crucial because we will have multiple vendors building silicon and building systems around ULink, and we would need these systems to connect to each other. And the amount of details in the ULink specifications, the definition of the protocol itself, which is very detailed, helps a lot to bring us very quickly to a real adoption in the market. So keep it simple. It helps the silicon design. It reduces power. It reduces complications. It shortens the design cycles of silicon, which are typically quite long. And it also helps the cross-vendor interoperability.
Perfect. And in what ways might CXL and UALink work together, and where might their roles differ?
Good question. So CXL is a resource. It can serve to multiple things. First of all, it can serve as a memory resource. For example, when the UniFabrics memory switch uses memory resources, it could use mainstream DRAM or use CXL memory as one resource. It can be used on the host itself. CXL memory that augments the DDR on the host, which is available to the accelerator. And CXL can also be used as the native interface between the accelerator and the host itself. Today, most implementations use PCIe, and PCIe is I/O coherent or non-coherent. But if you look further, there are a lot of opportunities in making this type of connectivity coherent using CXL.cache and CXL.mem, where the host and the accelerator see a coherent view of the local memory that exists in the system domain or the OS domain. So CXL helps a lot in creating this coherency and in bringing more memory resources into the ULink ecosystem.
Excellent. Next question, does radix of the UALink switch change or increase with the inclusion of this new memory fabric?
The memory fabric itself connects natively to the UALink switch, meaning it connects to standard UALink ports, and it connects as another accelerator. This is how it looks like an accelerator with a giant memory. So depending on the topology of the system, it looks like connecting another accelerator. There are several ways to have the memory injected in. One way is having it through the UALink switch, and this comes natively through the UALink domain. And another way is to put the memory pool on the host side, such as a CXL memory pool, and inject it through the connectivity that the accelerator has to the host side. Here, what we see is where the memory comes through the UALink scale-up domain, and here it consumes standard UALink ports.
Perfect. I think we have time for one more question. So the last question is, when will we see the first silicon with UALink?
Actually, there is a first silicon with UALink. It's in prototyping and development. There would be a lot more to see in next year, 2026.
Excellent. Well, thank you for your time today, Ronan. That was our last question that we have for today. So thank
Thank you.
you again to Ronan. To the audience, the webinar recording will be made available on the UALink Consortium YouTube channel, and the slides will be available for download on our website. And thank you very much.